Hi,
Hello.
I'm Dan Brown from the University of Washington, where I can report the air quality index is 70, which is in the moderate range. We've been through a weekend of some higher air quality index values, and that relates back to my comments. I'm here to comment from the perspective of, and I don't have slides, so I'm just going to talk as a panelist here in response to this notion of digital twins and the rich information we got from both NOAA and NASA on the work that's going into building the systems to deliver data integrated with models. And I want to reflect on that in the context of a kind of a research application ecosystem around fire, wildfire, in which my initial report of the air quality index indicates that we sit in the middle of it out here in Washington and Seattle, and we're in fire season here. And I am not directly involved in fire research myself, but I am connected to a number of the folks who are, and I want to reflect on some of the things that they're doing and some of the ways in which that connects to this notion of digital twins. In particular, we have collaborations with the Department of Natural Resources out here in the state of Washington. The U.S. Forest Service has a research group as well as operational groups out here in the region. University of Washington researchers in numerous departments working on fire at various levels. And I want to sort of break down the ways in which digital twins connect to this problem of fire. I also want to recognize that there are federal groups, the National Wildfire Coordinating Group, working on bringing geospatial data together in order to bridge essentially this research need that combines digital assets, both, and I was really glad to hear Dan's comments about the integration of data and models. We have this rich collection of data, and I know when NOAA talks about data, included in that is model output. And so models produce data as well as observational assets producing data. And so we're bringing together data and models. Ultimately, in my view, and in the context of the wildfire issue, is to support decision making. And the question then, in my mind, and I'm not going to be the one to provide a definitive definition of digital twins. I'm still sort of struggling with it myself. But one of the things that I believe about the kinds of digital assets that are going to help decision making is that they're scale dependent. And I recognized in Dan's talk this notion of multi-scalar digital twins is built into the concept. Whether or not those are separate digital twins for different kinds of scales is kind of a question in my mind. And I think the scale question comes down to both spatial scales, the extent as well as the resolution needed to answer the kinds of questions, as well as the temporal scale. And Dan Duffy alluded to this notion of, are the forecasts that we're going to get out of digital twins, are they a couple of weeks, are they a couple of years, are they a couple of decades? And I think that's particularly relevant in the fire context. And I want to provide some examples here of four sort of categories of decisions in which digital twins and geospatial data and models generally have a role to play. And start with the sort of broadest scale of forest management, which is something that we do regionally and over regional landscapes. And we're focused in the forest management context over decades. Forests grow slow. Sometimes out here in the wet part of the Cascades, they grow faster, but they mature over decades. Fuel loads grow over decades. Their fire risk is affected by their previous burn history, previous management history, and structure for certain. And so data, we've got a lot of folks out here using, and everywhere, using LiDAR-based data to characterize forest structure. Dan had a nice graph of mapping individual trees and getting height, and that kind of information goes into decisions about where do we have forests that are overstocked, where the risk is higher, and that intersects, of course, with climate, which is a decadal process as well, that we're going to see changes over time. So we need to think about the management approaches that we take at the landscape level and the impacts it's going to have over decades. And then you have sort of getting finer time and space scale, a sort of strategic response. When we do have fires, we need to have assets in location, and these things kind of happen on an annual time frame. We're in the middle of fire season out here, and we have flight assets and personnel assets to fight fire. We have ownership information that impinges on who's responsible and where the assets can be located. And then we have the seasonal weather, the weather patterns happening on a seasonal basis, and seasonal forecasts affecting both exposure to the possibility of fire as well as the risk. And so we need to know where the population is, where the infrastructure is, where the assets are that are most sort of an immediate need of loss or immediate risk of loss. And then you have the tactical response during fire season on a daily basis. We need information at the landscape level of where the ignitions are, where the fires are, what the weather's doing. And this is clearly making a distinction here between weather and climate. On the decadal scale, we need climate information. On the tactical scale, we need weather information. Where's the wind blowing in particular, and how strong is the wind? And we've got folks working on that, trying to take the physics-based weather models and speed them up with AI-based tools to produce more rapid weather forecasts. And we need to integrate that with the infrastructure and the assets, and devise attack plans and prioritize the use of the assets, because the fires can often be more numerous than we have access to attack them. And then finally, the sort of fourth decision element in this ecosystem is smoke. And that's something that we think about on an hourly basis. And as a regional problem, we know that smoke is carried in the atmosphere. So we need information there about the fire. We've got folks in the U.S. Forest Service Fire Lab here collaborating with the University of Washington on modeling fire, the fire itself, modeling how the constituents in the smoke get picked up in the fire, and the vortices that are formed and carry the various constituents aloft, modeling what is in the smoke and what we're exposing populations to. And then, of course, the weather modeling that helps us predict where that smoke's going to go, which population centers are going to be affected. And of course, there are some big population centers and some smaller population centers, and we know that smoke impacts are disparate impacts on different populations and so forth. And all of that, the sort of forest management, strategic response, tactical response, and smoke response sort of all interacts with and feeds back to as well updating the fire history, which is sort of this long time record of affecting the status of the ecosystem and the vulnerability as it interacts with weather and climate. So there's just some thoughts that I have specifically related to how do we think about the context of digital twins as a tool to affecting decisions on the ground. And clearly it is a multi-scalar challenge. I don't know the answer to this question of whether that's one digital twin or multiple digital twins for multiple purposes. We've always thought about models and data in the context of fitness for purpose. I would think that we want to think about digital twins in that way as well, which might mean we have an ecosystem of digital twins.
Thank you, Dan.
Of course, we're here at sea level, and even our university campus is only a few feet above sea level. We have recurrent flooding of the enormous diverse array. This is a king tide flood event shown at an adjoining neighborhood. You might see some streets low-lying streets being flooded there in the foreground at the bottom. And, this presents a very complex but systemic threat. It's been documented over more than 100 years, and it's now being projected with increasing confidence and still looming uncertainty. So it gets into that kind of confidence and uncertainty in future projections. In the background is downtown Norfolk. This area is about 2 million people. That is kind of the oldest kind of core central business district. We have the world's largest naval base, one of the world's largest natural harbors in the area. We have sea level rise projections. This is kind of a multitude of them. The upper curves are increasingly the ones being adopted. And towards a digital twin approach to these problems, we have been harnessing geospatial archives, building flood sensor networks and assimilating those data, and then the increasing volume of available models and satellite imagery. So here is a rendition of the same area in reality being flooded in a flood simulation, indicating categories of building risk and flood exposure. And I'll go into some of the complexities. Our cartoon diagram at the onset, really our proposal stage of this project, was to build in threads between actual reality, such as ongoing sensors and assets, and the digital representation or a replica of them, and to build feedbacks so that when we have, for example, a flood event, and then we get damage reports, we can assess, well, did we observe that? Did we predict that accurately? And then go in and fill those gaps, such as citing better flood sensors, refining the model grid, and building kind of feedbacks to doing better science, if you will. Also, a benefit has been mentioned by Daniel and others is the ability of foresight. And so here we are trying to put multiple timescales of a digital twin what-if questions. Timescales of near real time, such as decisions like evacuation, pre-positioning flood response efforts, and doing recovery, on to further out, in even decades out, where do we invest in mitigation adaptation efforts? So this is kind of that spectrum or kind of multiverse of our what-if questions. We are using other resources. Here's a NASA sea level rise tool coming out of, I think it's JPL in the team there, looking at the highest confidence of some of the future projections. So we're incorporating that. We're beginning to incorporate soon vertical land motion, which is coming out of various INSAR estimates of vertical subsidence here, and using that to deform the digital elevation models to project inundation in the future. And then we have our hub that sort of brings this all together, very localized, but this is in the cloud, centrally using AWS, Amazon Web Services, and we're pulling in NCEI, NOAA Digital Coast, USGS, flood sensor networks from NOAA, from the aforementioned, from the private sector. We're bringing in NASA satellite data. We've got a data cube that kind of is the focus of a lot of this assimilation. And then we have a variety of operational flood simulation models that we're also bringing in for comparison. We even have drones and IoT sensors being deployed in this vein. So here is a map at the bottom right of our flood sensor network. It's a multiple networks, actually. And this is something that we are going in and filling the gaps. Particularly for an equity environmental justice standpoint. A lot of flood sensors had been cited on the basis of kind of qualitative sense or opportunistic decisions based on city rights of way and property and major locations of bridges, not situated from a standpoint of risk necessarily, or especially from environmental justice standpoint. So the purple sensors are infilling that we have done based on consultations with emergency managers, National Weather Service, and some of the cities especially where model grids meet, such as some of the rainfall runoff models versus the tidal storm surge focused models. So we're into the nooks and crannies of some rivers. We are deploying drones to capture imagery of flood extents, but also to map bathymetry and then feed that back into a more fine scale flood model. So there's just a couple screens, and there's a map of vulnerability. You may have heard of the Justice 40 census tracts by the Biden administration, and others have deemed it the Infrastructure Act solves issues and not avoid these areas, but actually tune to them. So we are incorporating some of the flood sensors to address those gaps. Here's our bigger architecture. It basically includes data science on the cloud, modeling, geophysical, geoscientific modeling and engineering, geospatial modeling, and then on the right is kind of our push toward prototyping for decision support and stakeholder use. About a year out from now, we hope to do a third year of the project where we do emergency management and planning style exercises, harnessing our prototype. I'll give you a couple quick examples. You may know the National Elevation Data Set and various iterations of LiDAR DEMs. They have blue lines with permanent water bodies. We don't always do hydrocorrection for that, and as a result, we may have tendency to underestimate flood extents. So one initial effort of the project was to simulate fine-scale flood events, find areas that were flooding that were not predicted, and then to backfill or correct the actual elevation models to represent and allow that flooding to be predicted in the models. Another is combined flooding or compound flooding, where we have extreme rainfall events interacting with high tides. You have backflow and kind of the assimilation or combination of flood events. So here's a modeling that has gone in to assess that area. That was kind of shown in the title slide I used. And then what if scenarios in the future will address that, because we don't want to be surprised where combined flooding moves from a nuisance to a chronic, even debilitating hazard that is not currently represented in really any of the flood mitigation policies. So turning to the data science, we're building off of StormSense, a regional application that Virginia Institute of Marine Science and City of Virginia Beach have largely led. Sridhar and Derek may even still be on the call, but this is bringing the cloud, using the cloud to bring all of these sources of flood information together. We are harnessing the Open Data Cube technology to also bring in these data and especially Earth observation data. And then here is a current development where we're attempting to integrate a operational tidal flood model called TideWatch and bring that into the data cube to predict impact. So I'll just show you some prototypes here. This is where we read in this data in near real time. We chart the hydrographs of the flooding. We plot the maps using mostly like a Jupyter notebook environment in the Open Data Cube, and then we predict impacts of that. Once we have this prototype operational, we can actually provide this to decision support. And lastly, as Dan lastly kind of brought up, the challenge of scale and time and space is the future. So here is some uncertainty and confidence sort of boosting approach by sea level science, going back and forward through time using downscaled climate model data to predict the future sea level change, which then guides how we address that in these models. Finally, as we are gathering and doing a lot of data assimilation, we have a hub. This is using ArcGIS Hub technology, Pixel for Health, short acronym for it there. And this is where we happen to have assimilated lots of data. Let's share the data out for locals. And so this is our Pixels for Public Health. And I do want to acknowledge all the other folks here. I'll just kind of end there and go back to Dan's thesis there that really we're building one type of digital twin, an instance in a continuum or multiverse of other possible digital twins. So hopefully we have lessons learned at the end of our project and could go forward and inform others. I'll get back to Wendy unless there's other questions or comments.
Thank you, Dr. Allen.